Okay, so previous lecture we discussed about TTT diagram, particularly for an eutectoid steel. Now, in case of here, we'll discuss. Also, we discuss the how pearlitic transformation starts. In the previous session, we also discussed about coarse pearlite and fine pearlite. So, it is due to the cooling. It is due to the diffusion rate of the carbon. The morphology of pearlites are different. So cooling rate plays very important role. Suppose one sample you are let us go for some very simple experiment. If you heat and you take toy steel above 727 degrees centigrade, suppose for example around 850 degrees centigrade, and suppose one sample you are cooling in the air and one sample you are holding in the furnace itself, means you are cooling in the furnace itself. In that case, the cooling rate of both the samples are different. The sample which cools in faster way, you get fine pearlite there. And the sample which cools very slowly, you get their coarse pearlite. So you can see in case of coarse pearlite, you can see alternate lamellas of ferrite cementite. But here, there is no clear distinguish between ferrite and cementite. So it's a fine structure. You need to resolve this pearlite. You need to go at very high magnification by using optical microscopy, then you can get properly resolve it. So the pearlite transformation, so cooling rate in this particular type of transformation plays very important role. So transformation upon continuous cooling. So you can see it here. So this curve, so this dash line curve is nothing but our TTT curve. But unfortunately, in industrial application, it has no use. I'm repeating, unfortunately, in industrial applications, nobody uses TTT diagram because so TTT diagram is constructed based on the isothermal series of curves. So best practice in industrial practices, we need to cool it continuously. But in TTT diagram, we are not cooling continuously. We are holding the samples one by one at each different test temperatures. Remember na, how we constructed TTT diagram? So you are holding the sample below lower critical temperature, that is below 727 degrees centigrade for different temperatures, and you are determining the time for transformation. So by similar way, we have constructed this diagram, but you can see here up to this part only we have the diagram. Below that we don't have this part of diagram. So this diagram we call continuous cooling transformation diagram, CCT. So previously it was called TTT, time temperature transformation. But again, by performing the same experiment, we have obtained this diagram is nothing but continuous cooling diagram, CCT diagram. You can see it here in CCT diagram. If you look at this, so this was our pearlite. So pearlite plus bainite, then fully bainite. But here you can see our diagram is up to here only. So we don't have bainitic bed. So bainitic region in case of CCT diagram is absent. Why? Because in case of bainite, if you look at this, if you look at this diagram, so this diagram is a TT diagram. So dashed line, dashed curve is nothing but TT diagram. In order to form the bainite, we need to hold it here. But in case of continuous cooling, so this holding is not possible. You need to cool it continuously. You can see, you need to cool it continuously. So that's why bainitic transformation in case of this continuous cooling, it's very difficult. And you will not get bainite in case of continuous cooling transformation. Yes, there are certain alloying elements where Bainitic bay in case of continuous cooling transformation is also possible. So you will get, so this one bay is up to this point. You will get another bay here. So by doing addition of alloying elements, you will get one more bay, and this bay we call bainitic bay, and from that you can cool it and you will get bainite. So by this way also you will get bainite, but alloying elements, there are certain alloying elements where by addition of those alloying elements, so this bainitic bay, separate bainitic bay in some type of steels is possible, not for all the steels. In some type of steels this bainitic bay exists, and you may get their bainite, but it's very difficult. So regular practice is to hold the sample somewhere here, then you go for this. So this heat treatment we call O-tempering. O-tempering. So I'm writing by mouse, so may not be correct. So O-tempering. Okay. So here it is written. So in practice, TTT diagram are not applicable since under real conditions of heat treatment, the transformation occurs on continuous cooling. Hence, these diagrams can be modified by quantitatively useful for continuous cooling conditions. So this is just a simulation for you, so that you can understand how TTT diagrams are, how continuous cooling transformation diagram works. So here you can see we have here separate bay of bainite. So that's why I mentioned in the previous slide that in certain steels, separate bainitic bay can be formed. Now let us go at the first stage, that is around 800 degrees centigrade. Obviously we have their austenite because we are above eutectoid temperature. So that is homogeneous austenite, stable austenite. Now when you go for continuous cooling, now you are entering into ferritic region. So ferritic transformation starts. Obviously ferritic transformation starts for eutectoids. If you are looking at the eutectoid steel or hypoeutectoid steel, then austenite transforms fully into ferrite. Then pearlitic transformation starts. Now you are entering into bainitic region, so bainitic transformation starts. Sorry. So you are cooling here itself, so fully pearlite has been transformed. So ferrite plus pearlite mixture, you can see it here. Now how much time required? In 10 to the power 4 seconds. So medium cooling. So directly from austenite you are quenching into bainitic region, so you will get bainite. Bainite is now growing, it's growing continuously, and you will get 100% bainite here. Now you are going for fast cooling. So from austenite to directly martensite, you can see it is a lenticular type structure, lens type structure. It is a needle type structure. So lenticular, lens, needle, both are same. So austenite has been transformed. You can see within the austenite grain, you can see this lens or so this lens or needles of martensite. And we have here 100% or 90% martensite can be considered as 100% martensite. So in less than 1 minute cooling. So this steel is very hardenable. So 100% martensite or less than 1 minute of cooling. Okay. So this transformation is need to be understood. Now, just for proper understanding, let us consider this TTT diagram. So this TTT diagram is for eutectoid steel. Remember that for eutectoid steel again, martensitic transformation is possible because directly for less than suppose this is a critical cooling rate. So means around less than 10 seconds, less than 5 seconds, you will get martensite there. But in case of hypoeutectoid steel, so you will not get this kind of diagram. In case of hypoeutectoid steel, so this is our loop. So in case of hypoeutectoid steel, you can see here, so this nose of C curve is actually on the negative side of the time axis, or it crosses the y-axis. So in order to form the martensite, then you need to cool the sample in less than 0. That is impossible. So that's why in case of hypoeutectoid steel, you will not get martensite there. And similarly, in case of hypoeutectoid steel, you will not get martensite because hypo and hypoeutectoid steel. So this nose of C curve crosses the y-axis. So it's very difficult to get it there martensite because it's not possible to cool the samples in negative time. So what to do? So we need to push this nose of C curve to the right side. So we need to push it. So you cannot push by using your hand. So we need to add certain alloying elements. So by addition of alloying elements, this nose of C curve shifts to the right side. It shifts to the right side. Suppose, imagine that by addition of alloying elements, I will change the color. So I will take, let's take this. Yes. So by addition of alloying elements, suppose this is your nose of C curve. Now you can see it here. So you have so much of time available to form martensite. You can see around 10 to the power 2. In 10 to the power 2 times you can pull the sample. Still you will get martensite there. Are you getting or not? So means this nose of C curve needs to be shifted to the right side. Then only your hardenability will increase. Then only your chances to get martensite will increase. Okay, and how to do that? By addition of alloying elements. So chromium, nickel, molybdenum, all alloying elements shifts the nose of the C curve to the right side. But aluminium and cobalt, these are the only two elements which shifts the nose of the C curve to the left side. So only aluminium and cobalt, these are both elements which shifts the nose of the C curve to the left side. All other alloying elements shifts the nose to the right side. So you need to draw the eutectoid TTD diagram for eutectoid steel, hypoeutectoid steel, and for hypoeutectoid steel. So you need to prepare all the three diagrams in your notebook, and three diagrams are very important. Now similarly, in order to form here bainite, we need to hold the sample somewhere here and then go for, so quench the sample in between around 300-400 degrees centigrade, then hold it there for a long time, you will get bainite. So this cycle, heat treatment cycle, we call O-tempering, and by using O-tempering, bainite can be formed. But for martensite, continuous cooling is required. Okay. So these are the certain terminologies are very important. In the next session, we will discuss martensitic transformation.